Thanks for the introduction. Good morning. I'm Jianxing. Today I'm going to present our work, Phantora, maximizing code reuse in simulation-based machine learning system performance estimation. So this is a collaborative work between Duke and Meta. To begin with, machine learning, including LLMs, is increasingly useful in many scenarios, but also consumes enormous resources, computation power to training. So people have built various machine learning systems to support it. For such systems, performance prediction is very critical. Probably the most important reason is the cost of real-world tuning. You need to run your system on a real GPU cluster, which is expensive in many aspects. Another reason is could be resource planning. You need to make decisions maybe before the hardware is available, like to purchase, like which GPU or NIC to purchase, which spec do you want to meet, and how many of them do you want to purchase before you have them. And for such training system, performance modeling is also very difficult, as the current system may have many knobs and switches to tweak, like batch sizes per GPU, the combination of complex parallelization strategies, and their configurations. There could also be specific feature like for each framework, like a selective activation rate computation in Megatron that you can tweak. These configs combined together, that they may affect each other, results in a very large configuration space and a non-trivial performance characteristics, which is difficult to capture by simple calculations like roofline. So people have developed some simulation methods to address this problem. The first simulation method is trace-based simulation, where you start from running a system normally on a real cluster and enable some profiler or tracers to capture a distributed trace of the system. The trace may look like this. On rank 0, we have some communication events. On rank 1, we have some other events, and so on and so forth. The trace will go through some stages into events, which will be consumed by the simulator to carry out the simulation, and you'll get performance metrics from the simulator. One limitation of this method is the high cost of collecting the trace, because for each collection of trace, you need to run your system on a real GPU cluster with profiler enabled. And also, like raw traces are very hard to configure. For example, it's hard to turn a trace collected, let's say, with 64 GPUs, turn to that with to a trace with 128 GPUs with, let's say, a different parallelization. So to reduce the number of trace collection needed for exploring these configurations, current simulation methods will not directly use raw traces, but they will have a configurable workload in the middle. And there will be a workload extraction phase that turns concrete traces into a configurable workload, like the model layers, how parallelizations are configured, how they combine, batch sizes. And you can directly change configs like tensor parallel size or batch sizes. But this configurability also comes with a trade-off. As the simulator only supports detailed communication events, the abstract workload will we need to turn again into these detailed events through a scheduler. The scheduler is essentially a reimplementation of the framework. For example, if you want a tensor parallel to be configurable in the workload, you need to reimplement the tensor parallel in the scheduler to issue correct network flows to the simulator. So the more you allow to reconfigure in the workload, the more you need to reimplement in the scheduler. Push this trade-off to a limit, we got methods called mocked framework, like SimAI published last year. The user can directly supply a training config, and there will be a mocked framework, which will just act as a real framework like Megatron. But instead of calling real communication on GPU, it will generate events for the simulator to consume, and the simulator give you performance metrics. In this method, we no longer have trace collection, but whatever features you need to support need to be reimplemented in the mocked framework. So both methods have to reimplement some framework features, but with ML systems growing rapidly, there are constantly new optimizations, new features, or even new frameworks coming out. And simulators implement this way need to catch up with these updates, which will be a huge effort. So we ask this question: can we directly reuse the framework code for simulation? Basically eliminate the need for reimplementation. It comes with the two main benefits. The first one is less maintenance effort, because you no longer need to keep up with the framework code and update your code base. And second one is can capture specific framework features. Like, for example, each framework may have its unique features. And even for the same parallelization, let's say tensor parallel or pipeline parallel, it can be implemented slightly differently for each framework. So our answer to this question is we can do this. And in our work, Phantora, we propose the hybrid simulation method for this. Hybrid simulation means we integrate the simulator with the actual system, making the simulator running transparently on top of the simulator. On top, we have PyTorch unmodified, the framework, which is also unmodified, like Megatron, DeepSpeed, or others, and a slightly modified training script, which I'll also mention later. Inside PyTorch, we have a Phantora tracer that capture torch operators as computation events. Under that, instead of original GPU libraries, we have Phantora Nico and Phantora CUDA runtime to replace these original libraries. These shim libraries will not actually call GPU for computation and communication. Instead, they will interact with a concurrently running Phantora simulator. The computation and communication events will be sent to the simulator for simulation. And the simulator will use one GPU for kernel profiling and reply all the completion times of all the computation and communication events, and also other information for behavior emulation. To elaborate more on this architecture, there are three main components in the simulator: the event queue, the profiler, and the network simulator. The event queue is the core of simulation. In addition to standard event-based simulation, it will also provide virtual clocks, which will act as the simulated wall clock for all the participated ranks. It will also handle synchronizations between ranks for, let's say, collective communications and other necessary synchronizations. The computation time is calculated by profiling the operators using native PyTorch with one GPU. We will cache the profiling results by some performance-critical parameters like tensor shapes or other configurations. So for next time when a same operator with the same shapes or configs arrive, we can reuse the previous profiling result. The network simulator is actually a standard flow-level network simulator with maximum fairness to solve the completion time for each flow in the event queue. However, when integrating this loosely synchronized event-driven simulator with a distributed real-time system, there is a problem we call past events. Let's consider this case where we have two independent ranks running on top of the simulator. At the time T1, rank 0 wants to send some communication and ask the simulator for its completion time. Normally, the simulator would calculate time T1 prime and responds that to the rank 0. Then rank 0 proceed normally as if the communication has ended. But if another rank 1, wants to start another communication at time T2, where T2 is between T1 and T1 prime, and if they, like say, rank 0 and rank 1 share some physical links, then this communication from rank 1 will interfere with the communication from rank 0, making the previous completion time T1 prime inaccurate. What's worse is unlike static workload, rank 0 and rank 1 here are real-time systems running transparently. So the simulator have no idea whether another rank will have communication or when. However, in our case, as we focus on performance estimation, we found an opportunity to maintain accuracy efficiently. Our method is to optimistically proceed just based on the known states. And when there's a past event, we roll back and fix the simulator state to synchronize. So look back to the example before. The simulator first will just respond T1 prime as if there's no other communication. Then we have a network event at T2 between this interval. The simulator will roll back to the T2 where the past event begins and recalculate the completion time of both affected flows. Here we have flow from rank 0 and rank 1, both recalculated. And at this time, the simulator state will be at a clean state. And also this rollback will be very efficient because we have all the throughput history recorded the rollback will just be several calculations. The final step is to trace down the dependency graph and update other events start and completion time if they depend on the affected events. But in the example we show, we don't have other events. With the assumption that the time taken by a certain operator does not affect the system control flow, which is usually the case for machine learning training, this rollback approach can enable Phantora to deliver a correct simulation result finally. In addition to correct timings, transparent hybrid simulation also requires a correct emulation of all the CUDA library behaviors. This is the part that takes most of our development effort. I'll briefly show some points here and refer to more details to our paper. We implement VRAM tracking on CUDA malloc and CUDA free, so is correctly raised with respect to configured capacity, and the caching allocator behavior of PyTorch is correctly reflected without additional effort. We emulate the CUDA asynchronous programming infrastructure built on streams and events. We precisely manage the related dependencies and synchronizations, also correctly reflected all the overlaps, including computation overlap in the system. We also emulated the complex synchronization behavior in the NICO library, including NICO setup, all the collectives, and other operations. All the mechanism before makes a real system, machine learning system, being able to transparently run on top of Phantora with a small user effort. For example, a user could just simply install the frameworks unmodified and just add several lines to the training script to enable Phantora in their system. The logging scripts will also work like this. Here we show an example called snippet from Torch Titan. And when running with Phantora, it will just log all the metrics, all the performance metrics, as if you are running on a real cluster, except for the loss, because we don't have values. Now we are able to show an example of tuning a machine learning training system of different configurations. Here is a case study using Megatron under a limited VRAM setting. We compare methods of gradient accumulation and activation recomputation. We did not write specific code for this feature. They will just run transparently on top of Phantora. And you can draw this figure with only one GPU. The x-axis is peak VRAM usage, and the y-axis is the throughput per GPU. So at each capacity, VRAM capacity, the user is able to choose the most efficient configuration, like batch size, use which method, gradient accumulation or activation recomputation, and what gradient accumulation steps to use. We'll also be able to validate the Megatron's selective activation recomputation effect, where they save a lot of VRAM, and to enable training that will otherwise if you have very limited VRAM. In terms of the accuracy and speed, we show some results comparing with Torch Titan's public performance benchmark up to 128 GPUs. The simulation is done with one H200 for H100 clusters and one A100 for A100 clusters. We're able to have 2.9% average error and 8.5 maximum error compared to their report. And the simulation time is about 20 seconds maximum per iteration. So for the training system, usually, you only need several iterations for the performance, because every iteration is basically doing the same thing. So that means compared to running the system on a real 128 GPU cluster, we can get performance numbers using only one GPU and within a few minutes. For the scalability part, we run Megatron on top of Phantora with one H200 to simulate different number of H200s. The simulation time scales linearly, which is expected, as the number of events also scale linearly, and roughly at 1 minute per GPU, per iteration for 256 GPUs in our setting. With all the results about before, there are still several future directions to explore. So beyond tuning existing systems, we're also exploring to use Phantora for new system ideas, like new parallelizations, for tolerance mechanism, thanks to our hybrid simulation, and also hardware co-design, like possibilities like new accelerators, optical switches, etc. For further improvement on our network simulator, because currently we're just using standard flow level single thread simulator, We believe other methods could also be applied, including various methods proposed like, in this conference and the previous talk. Because we're using standard discrete event simulation, so methods like, say, parallel discrete event simulation, or maybe some machine learning-based approach, maybe fast-forwarding approaches, they should also be applicable. A more fundamental challenge for simulation overall is the value-dependent performance. For example, let's say in reinforcement training, the system performance is significantly affected by the response length of the model. But in simulation, we don't have the real response length values. One possible approach to mitigate this is to trade off transparency with accuracy. So we can let, let's say, user to annotate some distribution of these critical values, and we do some random sampling in the simulation. So in conclusion, we found that current machine learning system performance simulation, they all require some framework reimplementation. But direct reuse of framework code is achievable via hybrid simulation. And our implementation Phantora provides high fidelity estimation. We are able to achieve 2.9% average error compared to Torch Titan's public benchmark, and with a small user effort and almost complete support of all the framework features. We currently support 3 frameworks: Megatron, DeepSpeed, and Torch Titan. We believe that in our architecture, support new frameworks should be also very easy. And lastly, Phantora is open source at this GitHub link. Welcome everyone to use it, and feel free to contact us if you have issues or feature requests. And also welcome any performance ground truths that we can compare with and improve Phantora on. Thank you for your attention. I'm happy to take any questions.